Hello and welcome to Video Podcast 1.1. This vodcast is titled Rocks, Minerals, and Some Basic Chemistry. Let's start off by trying to understand the relationship between rocks and minerals. Now we're going to start with minerals, because minerals serve as the building blocks of rocks. Before I get to that point, what's important that you understand about minerals is that they have atoms bonded in regular, repetitive internal structure. I have a very simple Lego model that I want to show you to kind of illustrate what we mean when we say atoms are bonded in regular, repetitive internal structure. In this Lego model, the very top Lego is a long yellow piece. The next two pieces below, you have a green piece and an orange piece, smaller. And then we get back to a long yellow piece. So if you imagine that these are atoms in a mineral, you can see that they're kind of bonded in a regular, repetitive pattern, where if I show you this bottom yellow long Lego, you'd probably predict that below that one, if this were to be a larger mineral, you'd have a small green Lego here, and then a small orange Lego over here. So this model, quite simply, shows you that minerals are made up of atoms, because of course I can take the Legos apart and I have the individual components of the mineral. Now I'm going to use the exact same model to explain the relationship between minerals and rocks. So I want you to now re-envision this very simple model where instead of these pieces being atoms, I want you to think of them as different minerals. So these are three different minerals, and if we combine them together, we form a rock, because minerals are the building blocks of rocks. Just like atoms serve as the building blocks of minerals, minerals serve as the building blocks of rocks. A very common example of a mineral is halite, which you probably know as table salt or sodium chloride. As shown here in this image, you have sodium ions and you have chlorine ions. You see that sodium chloride, or NaCl, which is the chemical formula of the mineral halite, forms these nice little cubes. And when we see halite, the mineral, it often is cubic. Salt crystals love to take the shape of little cubes, and that's because of the orderly internal arrangement of the sodium and the chlorine atoms. The way they get stacked, they form a nice little cube. So halite is a great example of a mineral. Let's talk about granite, because I think that's a great example of a rock that you probably know from your everyday experiences. I've actually included a picture of a granite countertop that I put in my basement that I just finished. Granite's a really pretty rock, and it's a very sturdy rock. It can be expensive to put into houses. You might have granite countertops in your kitchen, or maybe you know somebody that has granite countertops in their kitchen. But granite, the rock, is composed of three primary minerals: quartz, hornblende, and feldspar. If you look at either the picture of my granite countertop or the granite rock shown in the picture below, you'll see some really darker colored minerals. Those tend to be your hornblende minerals. The lighter colored minerals are going to be either your quartz or your feldspar. Feldspar tends to be more of a tannish or orangish or sort of brownish colored mineral. And quartz can take on a variety of colors depending on the impurities in it. And that's true of any rock. I'm just using quartz as an example here. But hopefully this example kind of illustrates the role that minerals play in rocks. In order to define minerals, we're really going to look at 5 main criteria. The first thing is that minerals have to be naturally occurring. If you produce a diamond synthetically in a lab, that's not going to be classified as a mineral because it's not naturally occurring. Minerals also tend to be generally inorganic. When we use the term organic, we're referring to carbon-containing substances. For instance, glucose, the sugar your body uses as its primary energy source, has the chemical formula C6H12O6. There are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in each glucose molecule. Minerals typically are not going to be organic compounds. Minerals also have to be solid. They cannot be liquids or gases. So although it's kind of weird, water ice is classified as a mineral. The other 2 characteristics, minerals have to have an orderly crystalline structure. The example here I have in this image is the silicon-oxygen tetrahedron. You see that in the center of the tetrahedron, you have a silicon atom, and it is surrounded by 4 oxygen atoms. When we consider the orderly crystalline structure, you can actually see that the geometrical configuration of this tetrahedron looks like a pyramid in 3 dimensions. And it's important to know that the silicon-oxygen tetrahedron is the building block of silicate minerals, which we'll talk about in a later video podcast. Minerals also have to have a definite chemical composition. As an example, the chemical formula for quartz is SiO2, silicon dioxide. Essentially what I'm saying is you have to be able to write a chemical formula for the mineral in question. Okay, let's transition now to talk some basic chemistry. It's important that we know that atoms are the building blocks of everything. We're going to start off by looking at the nucleus of an atom, and that's at its dead center. We have two different particles in the nucleus, protons and neutrons. In the image shown, the protons are the red spheres and the neutrons are the blue spheres. Protons have a positive charge. What's important that you know, and I'll go over this more on the next slide, is that the atomic number of an element is the number of protons in its nucleus. Keep that in mind. Now, neutrons are electrically neutral. They don't have charge. So we said protons have positive charge, neutrons have no charge. They are also located in the nucleus. And when we consider the mass number for an atom, we have to consider both the protons and the neutrons in the nucleus. We essentially add them up, and that gives us the mass number of a particular atom. Lastly, we have the electrons. Electrons have a negative charge, and they're about 1,000 times smaller than the proton and the neutron. They're small, they're whizzing around the nucleus. Now, this isn't the best model because quantum mechanics tells us that it doesn't work as pretty as we'd like to say, but you can almost think of the electrons as being planets orbiting the sun, kind of buzzing around in a circle or an ellipse. Again, that's not a perfect model for how the atom actually behaves, but it kind of helps us make sense of things. Sometimes the electrons are also described as bees buzzing around their nest. So here's the periodic table. And for our discussion, what's important that you know is that the metals tend to be to the far left side of the periodic table, and the non-metals tend to be to the right side. Let's focus on just one element. Let's look at nitrogen. Nitrogen has a symbol of N, and that number 7 above the N represents the atomic number for nitrogen. What that means is there are 7 protons in the nucleus of a nitrogen atom. If there aren't 7 protons in the nucleus, it's not nitrogen, it's something else. Mass number can be a little bit more tricky. And to explain mass number, I'm actually going to look at a PhET simulation. So here we are at a awesome PhET simulation. In fact, you can see the URL for this simulation here on the screen. I recommend you try it out if you want to kind of play around and kind of grasp these concepts that we're talking about. The isotope we're going to start off by looking at is carbon-12. We're only focusing on the nucleus. Carbon, by definition, must always contain 6 protons. That never will change if we're talking about carbon. So what does the 12 represent? 12 is the mass number here, and the mass number is the sum of the protons and the neutrons. Carbon-12 would have 6 neutrons to go along with its 6 protons. You see that in nature, 98.93% of all carbon atoms are carbon-12. But what if we add another neutron to this nucleus? We now have carbon-13. Carbon still has 6 protons in its nucleus, and about 1% of the carbon atoms that exist are carbon-13. That's why when you look at the periodic table, the atomic mass number, the number under the C for carbon, is 12.01. It's a weighted average. Now there is one other consideration here we should look at, and that's carbon-14. Now carbon-14 is unstable, and we use carbon-14 for radioactive dating because over time it will radioactively decay into a stable form of carbon. Our last little basic chemistry consideration today is about bonding. The 2 primary forms we're going to focus on are ionic bonding and covalent bonding. In ionic bonding, we're talking about the transfer of one or more electrons from one substance to another. We're going to consider the example involving halite, because halite is made of sodium and chlorine ions. If you find sodium, which has the chemical symbol Na, it's located to the far left side of the periodic table. This family is known as the alkali metals. And in ionic bonding, we're talking about metals reacting with nonmetals. So we know where sodium's at. And notice that it's in the very first column. It has 1 valence electron, meaning that there's 1 electron hanging out in its outermost electron shell. And if you want a really simple way to know how many valence electrons there are for the main group elements, in the second column, there are 2 valence electrons for each of those elements. Let's go over to the column that you see Roman numeral 3A. They all have 3 valence electrons in that family. 4A, 4 valence electrons. 5A, 5 valence electrons. 6A, 6 valence electrons, and you kind of get the point. The far right column are what are known as the noble gases. They are absolutely stable. They're inert, they don't really react because they have the most stable possible electron configuration. Now, all other atoms want to get to a noble gas configuration because all atoms want to be stable. So sodium, with that 1 valence electron, knows if it can get rid of that 1 valence electron, it would have the electron configuration of neon on the periodic table. And neon has a stable configuration. So sodium wants to give away its valence electron. Look at chlorine. Chlorine is located to the right side of the periodic table in that yellow region, and chlorine is a nonmetal. Chlorine is what's known as a halogen, and halogens are extremely reactive nonmetals. Those two families have a match made in heaven when it comes to ionic bonding. Chlorine has 7 valence electrons. It wants to get 1 more valence electron because then it would have 8 valence electrons. And guess what? 8 valence electrons is what argon has. It's the element right next door to it, and that is a stable electron configuration. So if we come back and look at this picture, for ionic bonding to occur in halite, we have to see sodium give up its 1 valence electron to chlorine, and when they do that, we form a very nice cubic lattice of sodium and chlorine ions, and that's a great representation of the halite mineral. It's also a great representation for how your table salt looks too. The other main type of chemical bonding is covalent bonding. Covalent bonding is the sharing of 1 or more pairs of electrons. Covalent bonding is not typically bonding that occurs between a metal and a nonmetal, and the simplest case we're going to consider is diatomic hydrogen, H2. A hydrogen atom can bond with another hydrogen atom, but it doesn't make sense for there to be a transfer of electrons because one of the hydrogen atoms will not have a noble gas configuration if it has no valence electrons at all. What hydrogen does covalently is it will share its valence electron with another hydrogen atom, and then when that happens, if you look at the hydrogen atom on the left, it can claim it has 2 valence electrons, and the hydrogen atom on the right can also claim it has 2 valence electrons. And if we go back and look at the periodic table, the noble gas that has 2 valence electrons is helium, and helium is a very stable electron configuration. So a hydrogen atom can covalently bond with another hydrogen atom to help both of the hydrogen atoms get to a stable electron configuration. Although I'm not going to go into detail on it, there is a third type of bonding known as metallic bonding. That's extremely important when we look at that transition metal region. So some of your elements like copper and gold, as just 2 examples, are great conductors of electricity because of metallic bonding. Metallic bonding allows for the free flow of electrons through the substance. And that's why we use copper for our electrical wiring in most everyday situations, because copper is really good at allowing electrons to flow from one copper atom to the next copper atom. And of course, the flow of electrons is electricity. Okay, thanks for watching. If you have any questions, comments, or concerns, feel free to bring them up in class, and I'm happy to explain whatever I have to explain. In the meantime, feel free to rewatch this video, jot down some notes, play around with that FET simulation if you go to the URL shown on the screen while I was playing around with that, and I'll see you in Vodcast 1.2.